All right. Hey, everybody. So today we're doing topic 24, regularization, which is basically the fancy word, the data science word for combating overfitting. If you have overfitting, and this is actually a pretty common interview question, how do you combat overfitting? It is through any regularization process. Regularization is sort of an umbrella term for all of the processes that help to combat overfitting. And we're going to be talking about two of them in the realm of linear regression today. So before we get into it, I just want to break down today what I'm going to talk about is regularization, but also as part of regularization, I'm going to be talking a little bit about how we combat for data leakage with when you're doing different scaling. I think I saw a couple of you added these into your projects, but it wasn't really in our curriculum last phase. So I do want to point out several things that will help with data leakage as well. Okay, so to start, regularization, a technique used to avoid overfitting, as I just mentioned. Typically what happens in a regularization process, it discourages overly complex models by penalizing the loss function. So loss function is right now, for our purposes, it is interchangeable with cost function. And yesterday we talked about cost function and how for linear regression, our cost function is the sum of squared error between the points and your model. So by penalizing the loss function, you can actually discourage over complex models. And we'll talk about how that happens mathematically and also when you apply it to a data set. So at the end of last phase, we talked about the bias variance trade-off, which is really just the trade-off between over and underfitting, model complexity, your overfitting versus underfitting, and your predictability or model. All of these things coming together are part of getting that bias variance trade-off and balance. So a couple other diagrams, I think I talked about this one before, when you have low bias, high bias, low variance, high variance, what do those typically look like? So if you have a high bias, you have systematic errors in your predictions. Your bias is about the strength of the assumptions the model makes, and underfit models will tend to have very high bias. When you have high variance, your model is highly sensitive to changes in data, and overfit models tend to have low bias and high variance. So if you did any of like the cross validation, or if you did any of like the multiple train test splits during your project, you might have been looking out for high variance because you don't want your model to be very sensitive to changes in the data. You want your model to be general enough, depending on your context, to work on any subgroup of data within whatever context you decide that you want to apply your model to. So another different diagram to show off the bias variance trade-off. Here you have an overfit model, an optimal model, and an underfitting model. So if you have an underfitting model, it fails to capture a lot of the information in your data. A lot of information is just left on the table there. And overfit models tend to fit to a lot of the noise in the data and fail to generalize. So again, we talked about this at the end of last phase. How do we know if our model is over or underfit? You're doing your train test split. You look at your testing error and how it compares to your training error. And again, as model complexity increases, so does the possibility for overfitting. So actually, when you have more features, and that's what they mean by model complexity in this context, the more features you have, you'll notice, as I mentioned, the R squared tends to go up as your model tries to learn as much as it can from many different features. It might have it does have a higher tendency to overfit to those features. So that's the whole spiel about bias variance trade-off, which we did talk about last phase. It's a very, very highly conceptual thing. That's something that I want to mention as well. Like, it is one of the most common data science interview questions, the trade-off between over and underfitting. And it is really, I feel like a good way that you can answer these questions is really through context. So in your upcoming project, or maybe if you want to think back about the project that you just did, what is your bias variance trade-off looking like? What is your train error in relation to your test error looking like? Is there overfitting in your model or not? So questions to think about. We'll get into more of this practice in the weeks to come. All right, so Ridge and Lasso are the methods of regularization specific to linear regression. I know that there are a lot of math equations here, but I'll actually break these down. They're actually not as intimidating as they look. But Ridge and Lasso are two methods of regularizing linear regression. So there are two examples of penalized estimation. What penalized estimation does is it makes some or all of the coefficients smaller in magnitude, and some penalties have the property of performing both variable selection and shrinking other coefficients. The idea behind Ridge and Lasso is if you have like a really high coefficient for some feature, it tends to see that as potentially overfitting your model to that feature. And so Ridge and Lasso models won't let any coefficients get very large, because it'll then start to penalize your model for that. So usually when you have Ridge or Lasso models, your coefficients will all be around the same range. So this is what the cost function looks like. I know yesterday we talked about cost function, but I never really drew out any equations. But let me just annotate some stuff here. Let me zoom in first. Why are we not zooming? There we go. Okay. So we have our two cost functions for Ridge and Lasso, which look kind of similar. There's one key difference that I'll talk about in a little bit. But I want to point out which part of this is the same cost function that we had for our regular linear regression. So there's actually a couple different equations here. This part here is our sum of squared error. This is the same cost function that we were actually using for our linear regression before, because this is really just the actual y minus your predicted y squared error. So if you ever calculated and most of you, I believe, calculated your mean squared error in your project, for your mean squared error, this is really what you're doing. That's your cost function. So this is the cost function for just your regular linear regression. It becomes a little bit more complicated because we want to penalize the large coefficient terms when you have Ridge and Lasso. So let's talk about Ridge first. I mean, you'll see that they're actually very, very similar. But actually, let me talk about this first. So this is equivalent to this second part. The only change is instead of y hat, you have just your equation for your linear regression, your coefficients multiplied by the variables. So that is your linear equation there. So again, equivalent, but you have this added part at the end. And that's why they say penalty term or penalized estimation. So what this is doing, so in this equation, your m, and let me just draw some more arrows, m refers to your coefficients. So what's happening to our cost function here? So rather than only solely looking at the error between your estimated and your actual values, you're also looking at the value of the coefficients and you're adding that to your cost function. So your overall cost function is just going to have a greater value because it's going to take the square of every coefficient. And it's taking the square just so that negative and positive magnitudes are both taken into account. And also the bigger coefficient, the greater its square will be relative to a smaller number. So if you have like a very, very large coefficient, it'll penalize that pretty greatly. So as you can see here, m is going to just take every coefficient you have. And I know for the housing prices project, your coefficients could range from like negative, I don't know, from like 0.00 something all the way till like the 1,000. I think I saw a couple coefficients that are in the thousands, sometimes 100,000. So it's literally going to square each of those coefficients, and that will be your overall cost. So what your model will do in this gradient descent process to try and reduce the whole cost function, it's going to optimize not only the model fitting your data points, but also trying to balance that along with having your coefficients not getting too big. Any questions about that concept? Well, I know this is a brand new concept, so maybe I'll wait a few minutes. But yeah, the whole idea here is that we're balancing fitting your model to your data points with also not having ridiculously large coefficients. And similar happens with Lasso here. As you can see, the only difference between Ridge and Lasso's cost function is that whereas in Ridge, you're squaring each, you are squaring each coefficient. In Lasso, you're just taking the absolute value of your coefficient. And with when you're taking a absolute value of the coefficient, and this is kind of more mathematical, but with Lasso, we'll actually see in a little bit with Lasso, there is a higher propensity to make your coefficients become 0. And so automatically, it's actually sort of performing some level of feature selection for you. Because when some coefficients are 0, then that means that there's no relationship between the feature and the target. You can pretty much drop those variables. And we'll see that in action in a little bit. Main point I want to get across here is they're penalizing large coefficients, and that is added to your cost function. So not only is it helps overfitting because its main priority is not only trying to fit the line to your data points anymore, you're also at the same time trying to balance having these okay number coefficients. All right, so we are penalizing large coefficients. What are the effects / implications of that? So to think about this, some of the features that we had in our project include, just to name 2, there's square footage, and then there's also waterfront. So the coefficient that a lot of y'all were getting for square footage is around like the, I don't know, the $10, $20 range. Like when you increase your square foot by 1 square foot, your price will increase by like maybe $10, $20, which makes sense. So your coefficient is going to be like 10, 20. However, waterfront was a dummy variable that only took the value of 1 or 0. So if you have a waterfront, I think some people were seeing like your house value increases by what, like maybe $20,000. And so just naturally, the coefficient for waterfront is going to be much, much bigger than your coefficient for square footage. And this is where standardization comes in. I didn't really go too much into detail about this last phase, but the reason why we standardize is so that we can level all of our features. We can look at all of our features on a level playing field. We can look at their relative impact on your target variable, taking away the fact that square footage can take values in like the thousands and waterfront can only be 0 or 1. And so it's very, very important that when you're using Ridge or Lasso regularization to first standardize your data, such that it is all on the same scale. So regularization is based on the concept of penalizing larger coefficients. So if you have features that are on different scales, some will get unfairly penalized. Like for example, in the example of waterfront and square foot, waterfront is just going to get penalized really greatly because the coefficient for waterfront is like 5 digits versus like a 20 coefficient for your square foot. So a downside of standardization, as some of you have seen in this project, is that the value of coefficients become less interpretable and must be transformed back to their original scale if you want to interpret how a 1 unit change in a feature impacts the target variable. I'm going to send out a couple, I know I said I was going to send out resources yesterday, but I'm going to do it today. I'm going to send out some resources about that as well, of like reverse transforming, because now we're going to have better tools to reverse transform. Okay. Questions about anything I've said so far? I know I'm introducing like a brand new concept, but anyone have any thoughts?
What is in both cost functions, what does the lambda stand for?
Oh, that's a good question. Yeah. So lambda is just a constant. I can't believe we forgot to talk about that, but lambda is just a constant number. It can be any number, and you'll see in your, you'll see when we get to the coding of Ridge and Lasso in a little bit, but it just tells your model how much to balance fitting the model versus these coefficients. So if you have a very high lambda number, it's going to try and reduce your coefficients as much as possible. But if you have a lower lambda, it's just going to say, okay, let's just balance out our coefficients just a little bit so it's not super overfitted, but it's going to still prioritize fitting your model. So the lambda basically helps you set the balance between how much your model prioritizes fitting the model versus making your coefficient small. In other words, lambda pretty much dictates how much you want to regularize your model. That's a great question. I can't believe I forgot to mention that.
I have 2 questions.
Mm-hmm.
First question is, if the lasso regression helps with feature selection, should it be used towards the beginning of your process?
That is up to you, I would say. Like, it is definitely possible that you can like just use Lasso at the very, very start, and then you don't have to look at like maybe half your features because they brought it down to 0. However, it's sometimes you have to think, these models are doing this gradient descent mathematically, purely mathematically. So let's say you throw all of your features into a lasso regression and you decide to cut out half your features without even trying to like maybe do like a log transform or like maybe some polynomial features or interaction terms that could have you still include those features, you would just lose out on all of that. So it really depends on your process and whether it makes sense. Some people do use lasso at the start for things that are like maybe like 1,000 features big. Then that makes sense because you just don't have the capacity to look at every single one. But yeah, it really depends on the context of your project.
And also, is the like standardization, is that like common practice when you're doing any machine learning? Like no matter what, you'll be using it, or it's not?
Yeah, that's another good question. In the weeks to come, we'll see that some models require standardization, whereas some don't. Ridge and Lasso do require standardization just because you want the coefficients to be around the same, or you want your coefficients to be around the same scale. So because of that, yes, but there will be some models that we'll talk about even next week. Yeah, next week there'll be some models that we talk about that don't, the standardization won't make a difference.
Okay, thank you.
You're welcome. I'm also going to send out, I'll send it out today, but it's more relevant to next week's stuff. I'll send out a table summary of every model that we're going to touch on and things that you have to keep in mind when you're using each model. So I think that'll be a little bit more helpful to like keep track of what is important or when do you standardize and when do you not. Okay, cool. Any other questions at this point?
So just to summarize, the cost ridge function versus the lasso function, the ridge function is just more sensitive than the lasso function?
I don't know about sensitivity. I guess it's more sensitive to very large coefficients. So the penalty for very like numerically large coefficients is going to be felt more by ridge. So I guess in that sense, yes, a little bit more sensitive.
I'm
and
just
also,
yeah, like I guess the context is like when you would use one versus the other, or would you use them both, or etc.
Oh, okay, yeah. I would say if you know that your model is overfitting and you don't know whether to use Ridge or Lasso, it is quite common to just try both. If you already have some like, maybe you know in your mind that, okay, I definitely want to cut out some features, you would use Lasso. But if you say like, okay, I kind of still want to account for all of my features, or maybe I just want to study the impact, the relative impact of all my features with regularization, then you would still do Ridge. So it's not uncommon to try both and just see their results. And I'll show you in a little bit, the code is actually quite straightforward. So it's not a heavy lift to like do two different models.
Gotcha. Okay, thank you.
In a little bit, I'm also going to talk about like how the linear regression assumptions relate to this. So if I forget to say that, if I forget to mention that, someone remind me, please. Cool. The next thing that I want to talk about is, because we're talking about having to scale your variables, is scalars. And I don't think I mentioned it during phase 2, mainly because we're going to use it a lot more in phase 3, and phase 2, there's already a lot of stuff that we were talking about. Scikit-learn has these built-in scalars that are actually very, very easy to use and are built in a way that helps you prevent data leakage. So here I've actually linked the documentation for 2 of them, min-max scalar and standard scalar. Again, these are the 2 that are most commonly used. If you don't remember, min-max scalar just takes like your minimum maximum value, those will become 0 and 1, and everything else in between will get pushed together. And standard scalar takes the value minus the mean divided by standard deviation. Both of these scalars are based on the distribution of your underlying data. So for example, if you were to do a train test split, the min max of your train set is going to be different from the might be different, but likely will be different from the min max of your entire data set. And so scikit-learn has really, really neat built-in functionality to prevent the data leakage. Same for standard scalar, right? The mean of your train set is going to be different from the mean of your entire data set and the mean of your test sets. So I just want to point out certain things here. So min-max scalar, and it's exactly the same for standard scalar as well. And you're also going to get really used to reading scikit-learn's documentation, because this is going to be the main library we're going to be using for the next maybe 2 phases pretty much. But want to show you all that how we can use the scalars. So scikit-learn's documentation is really nice. I personally is one of my favorite libraries documentation because it's I think, really well organized. But you can just import the scalars from scikit-learn.preprocessing, and they actually have a bunch of other scalars as well. And what you can do is, how you use it is you have to first instantiate the scalar. Since we talked about object-oriented programming at the start of the week, we know what instantiation is. It just creates like an empty scalar. And then what you can do is you can fit the scalar to your data. I'm going to run through some coding examples later, but when you fit your scalar to your data, the scalar kind of remembers the min and max of whatever data you're fitting it to. What that means is you can fit it to just your train set, and this scalar object is going to remember the min and max of your train set that you can then apply onto your test set in this really neat way. So here you can see that in the methods, there's .fit. There is fit transform, which I'll actually show you all how to use fit transform in a little bit, because that's the one that's typically used. And there's also transform. So transform and fit transform are the two that you're probably going to be using the most for all scalars. Transform basically will take the parameters that your scalar remembered and just apply it to your other data set. So we'll see in a little bit, you usually fit transform on your train set, transform on your test set. So let's say the min and max of your full data set is 0 to 20, but then for your train set, it is 0 to 15. So if you fit your scalar on your train set, 15 will be 1, right? 15 will get a value of 1. But when you transform your test set, that value of 20 is going to have like a value of like 1.3, something like that. So so yeah, that's what I mean by it remembers the parameters of your train set that you can then transform your test set. It's actually really, really neat. I wish we had the time to talk about it last phase. But yeah, any questions about this? We will go through a coding example in a little bit, but any like questions about this part? Cool. Since we're here, scikit-learn also has a version of get dummies known as Hot Encoding. I think it was in some of the labs from last phase as well. But Hot Encoding is actually a safer way to do get dummies that also prevents data leakage. So for example, if you have like 10 zip codes as a categorical variable, and in your train test split, you only account for like 9 of them in the train set, that 10th one that was unaccounted for in your train set will not be accounted for in your test set either, even though it might be in your test set. I don't know if that made sense, but again, just prevents data leakage when you're like creating dummy variables. So scikit-learn is built in a way to really account for and help stop that data leakage. All right, so back to the code, and it's very similar for standard scalar, by the way. We're going to import a bunch of these libraries. So you can see here I have my errors. I'm going to do a linear regression because I'm going to just through this notebook show an example of a very, very overfitting linear regression and show how regularization helps with that. We have our standard scalar, Hot Encoder. That's the one I was just talking about. It helps you prevent data leakage when you're doing get dummies. And then there's also simple imputer, which is actually pretty neat. I'll show you all what it is in a little bit. So what we're going to do here is we're going to use a different housing data set. To be honest, forget which data set this is. It's not the one from your project, but X has these values over here. Let's just take a look at the columns. Looks like there's a bunch here. Looks like there's first floor, second floor square footage, a bunch of different features, but basically housing data set. This process is pretty similar to what we're used to. We split it, train test split. We're removing some of the features just because, and then do that in your train and test. So we're just keeping the continuous features for this data set. Now here's where I'm going to show the transformations on your train and test set, where you do like the fit transform versus the transform. So let me talk about this one first. So in filling in null values, prior to this, what we were doing is we're just finding the mean and then filling it in using, I think, a pandas function using the fill NA. But that there is also a version that exists in scikit-learn that will, again, help with your data leakage. So something that's really nice is if you have a strategy for imputing null values that is going to be consistent across your entire data set, you can use a simple imputer. So let's say any null value that I have in my continuous data set, I want to put in my median for those columns, you can do that. So what I'm doing here is I'm instantiating this simple imputer. And actually, let me pull up the scikit-learn simple imputer. You can see that there are a few different methods that you can use this. So the strategy for imputation, you can do mean, median, most frequent, constant. You can replace it with a specific value and other ways that you can do it as well. So what I'm doing first is we're going to instantiate the simple imputer. So at this point, the simple imputer doesn't know what to impute it with. Only when you're doing the fit transform is when it'll learn the median values for each column and then impute the null values. And it's fit transforming on X-train continuous, which comes from here, which is raw data, only the continuous columns. X-test imputed basically transforms your test set with the medians from your train set. So in just these 2 lines, or I guess 3 lines, that's what's happening there. So if we want to compare, oops, I know this cell has a lot of different things, but I'll walk through them in a little bit. If we take a look at X-train continuous, which looks like this, let's do like a is na.sum. Cool, there's like 58, 191 there. And if we take a look at the X-train imputed is na.sum, it should be 0. Oops. Oh, I guess that's an array, but pd.dataframe. There we go. Cool. So all zeros. And the column names are gone, but oh yeah, something else to note is that when you use a transformation, it turns it into an array, but you just have to switch it back into a data frame if you need to use it, which is less important for now. But yeah, basically train and test set for any of the columns, you're going to fill it with the median of the train set. So that prevents the data leakage there. All right, so what we're doing here, we're just taking the categorical values, filling the NA with missing values, and here we're using our scalar. So like I mentioned earlier, we're fit transforming on our train set. Oh, yeah.
So when you did the median, how did it know not to put it in the categorical?
Oh, that's just because we split it up here. So
with the features, right?
Yeah, so in this line here, we are only looking at the continuous features. So X-train cont continuous and X-test continuous are only the continuous.
Oh yeah, you did that there. Okay.
Yeah, sorry, that was I know I wasn't super clear when I explained that, but yeah, we're basically taking all the continuous features, doing this imputation, all the categorical features, which is this next step over here. These are the categorical features. We're filling NA with missing. And then, yeah, and then after that, we are doing our scaling. So scalar, because you don't really need to scale categorical variables because they're already 0, 1. In this case, we're only scaling our continuous variables, I believe. Yeah, imputed is only our continuous, which doesn't really make a big difference. So here we are fit transforming on our X-train imputed and only transforming on our X-test imputed. So we know that this has been scaled based on the parameters of our train set, which is neat. Cool. So now that all of our like data preparation is done, is it done? No, I guess not yet, but okay. First, we're gonna fit the model, I guess, on our scaled data, on our scaled continuous data first, I guess. So here we are fitting this model. Looks like we are using a 1 hot encoder to transform our categoricals. Looks like here we're putting together our train and test as well. And then we have our linear regression again. Okay, so I guess this might be redundant. Sorry about that, guys. So we have our categorical variables here, and then we are putting our continuous and categorical back together and fitting that all into our linear regression. So as you can see here, our linreg all is our model. Here we can get our train and test R squares. That's what we're doing here. X train all, Y train, X test all, Y test, and your MSEs and RMSEs. When I run this, you can see some pretty alarming results. So first, we have our training R squared that looks pretty good, 93.5. That's almost all of the variation being accounted for. but our test R squared is a very, very negative number. Now, a negative number R squared basically means that this model fits way worse than just putting a flat straight line through your data. So if you remember, an R squared is basically the relative explanation of variation in your target variable as compared to just taking the average for every data point. So this model is performing way worse than just guessing the average price, which is bad. And if you take a look at your training and testing RMSE values, you can see that training set, cool, you're only $20,000 off for each price of a house, which I think is pretty good. And then your testing RMSE is like, I don't even know how many digits there are here, but it's just bad. So this is a very, very exaggerated case of overfitting, which actually happens more than you think. But yeah, this is kind of exaggerated, but if you see values that are very different between your training and your test, it's an extremely clear sign of overfitting. If I were to like refit this model over and over again with like different train and test values, I'm pretty certain that like my coefficient numbers are going to be vastly different as well. So this highly, highly overfit. I know I went through a lot of process here. Any questions about this? I mean, this notebook is up on the repo as well if you just want to like break these into different cells and take a look at what the data is looking like. Also, I just uploaded the data set today because I forgot to do that earlier this week, just in case anyone tried to run this earlier. But yeah, any questions at this point before we get into Ridge and Lasso? Cool. One other thing to note is that going forward, all of the models that we're going to be talking about are going to come from scikit-learn, not stats models. I think with the exception of one, but most of the models that we're going to be using is going to be out of stats models. Okay, cool. So Ridge and Lasso, I've linked the documentation for both of them over here. And we're going to talk about a couple of things. But first, let's take a look and see how much better, just by using Ridge and Lasso, how much better our train and test errors look. So I'm just instantiating Lasso, which if you take a look over here, if you want to use Lasso, you can literally just do this. And I'll talk about alpha in a little bit, but you can just instantiate a Lasso model and do the same kind of fit. And I'm fitting it on the same data that I fit this last model on. So I did X train all Y train. Here I'm also fitting it on X train all Y train. And when I run this, you'll see that my values just immediately are a lot better. The R squared are both positive numbers, which is great. And our MSEs look a little bit closer together. I should take a look at the, let me take a look at the square root number, 0.5, 0.5. Cool. So yeah, both about $20,000, $26,000 off, which is a lot better than like this number that we were getting before. So just like that, we did sacrifice a little bit of accuracy overall. Like you can see that I guess our training RMSE only went up by like $5, which is pretty incredible. But our R squared is also a little tiny bit lower. Yeah, a very, very tiny bit lower. But now our test R squared, our test metrics are much more improved now. So just by changing our model from regular linear regression to Lasso, we've seen a great improvement in the overfitting. And as you can see, code-wise, very, very straightforward to implement. Any questions about this? Cool. All right, so next I'm going to talk about alpha. So alpha, what we have here, is known as a hyperparameter. And for different models, you're actually going to get different hyperparameters. And a lot of our process for this phase is going to be looking at different hyperparameters. So with Lasso, alpha is something that you can actually adjust just to see like what the effect of different alphas is. Usually if you take a look at, this is Lasso, right? Okay, cool. So in Lasso here, you'll see that the parameters are, oops, where's the alpha? Oh, I guess over here. So within here, these are different hyperparameters. Some of them have to do with different ways that the model trains, some of them don't. For Ridge and Lasso both, the only one that you really have to worry about is alpha. And by default, alpha is just 1. And here you see that alpha here, a constant that multiplies the L1 term. If we go back to our cost function, this is something that's kind of irritating with like data science in different libraries. Alpha is literally lambda. So whatever this number is going to be your alpha. So you can, what you're doing is you're basically adjusting how much your model cares about regularization versus fitting the data. So with an alpha of just 1, which was the default. So here the default is 1, which is why earlier when we instantiated with nothing in the parentheses, the default is 1. We already saw a pretty good improvement. So a process that we're going to get more and more into with different models throughout this phase is adjusting hyperparameters. So in this case, let's just try an alpha of 10. So with an alpha of 10, we see we get slightly different results. I wish I did RMSE for all of them because RMSE is a lot more interpretable. Let's do this real quick. Okay. With an alpha of 10, you can see that our train and test R squareds get a little bit closer to each other because we're adding more regularization and less on the model fit. So even though, yes, my train metrics get a little tiny bit worse. So you can see here we're at like 0.935, 0.934, and then our MSE goes down by like about, or goes up by about what, $250. But our test and train are now closer together. The fact that our test and train metrics are closer together just makes your model a little bit more reliable. And that is not overfitting to the train set, is unable to predict on the test set. So a very common process when you're doing any sort of machine learning modeling is, you know, checking for this, and with different values of alpha as well. So you can maybe do alpha 10, maybe you want to see what happens if we have alpha 30. Alpha of 30, you can see that these get even closer, but you are starting to give up some of your root mean squared error. This should be root mean squared error. Let me just quickly add that there. You are giving up a little bit of your root mean squared error. It goes from like 20,000 to 21,000. So it's really up to you to decide. This is the bias variance trade-off. How much of your accuracy are you willing to sacrifice so that you don't have an overfit model? Cool. And there are automated ways to go about this that we're going to talk about next week as well. Cool. Now with Lasso specifically, mentioned that Lasso is another way to do feature selection. So I know that this data set has a lot of features. So if we just take a quick look at and see how many features we have, xtrain all dot columns, that work? Cool. We have 296 features just because we have a lot of dummy variables in this data set as well. So 296 features is a lot. So let's see how many of them were brought to 0, which is basically like not relevant to our model anymore. So here we're doing, oh, I guess I could have done that as well. Total number of coefficients is 296, and coefficients that are close to 0, so less than, here I'm doing 10 to the power of -10, 117. So just like that, if you want, you can go in and just figure out which coefficients those are, get rid of those features, rerun your model. Your results shouldn't change by much at all. But then it'll be a little bit more efficient, especially if you have a very, very large data set. So that's one way that you can do lasso feature selection.
Right, so the only reason to get rid of features really would be to like make your model more efficient.
Yes, definitely. If you have like a bunch of 0 coefficients, it makes sense to get rid of them, just so like your model in this case will take half the time to run because it's doing gradient descent over half the number of features. Yeah.
But being in the model or not being in the model doesn't really change it.
Yeah, because the coefficients are 0, it's not going to affect it's not going to affect your RMSE. I don't believe it will affect your R squared, but RMSE will definitely be affected almost not at all.
Okay. That's interesting.
Yeah, super interesting. Okay, so that is Lasso. Next is Ridge, which is basically the other one. And Ridge, what we have here, when we run it with alpha equal to 10, you can see a very similar effect. Your train and test R squareds are much closer together. Let me just do the same thing again. Oops, not 2, but 0.5. Cool. Here you can see that we have a more regularized model just compared to what we had at the start. And as you can see, Ridge and Lasso both at alpha equal to 10 are going to give you slightly different results just because the way that they're doing their gradient descent, you have a different penalty term. And that just results in different coefficients and different R squared and RMSE.
Just a random question. Is there a reason you use 10 to the power of -10 instead of 0?
Oh, yes, because some coefficients, especially if you're doing a gradient descent process, the gradient descent doesn't always bring it all the way down to 0 because of learning rate. What learning rate does is it always changes a coefficient by some proportion. So it pretty much never reaches exactly 0. I think if you try and do 0, I'm not sure if this will give you something different. Yeah, it won't give you there, because if it's less than 0, there's negative. Yeah, that's basically why. So that's why you do some arbitrarily small number.
Equal to 0?
Ooh, that's a good question. Let's find out. Oh, okay, 116, which is different from 117. So I guess one of them is like 10 to the power of -10, which I guess that's something you can play with as well. If you just want to set like a cutoff, you can do that as well, just because the impact on the target variable will be very little. But yeah, I guess you could do this too. But I think earlier was 117, but not a big deal at all. Cool. So that's Ridge and Lasso. If you saw some of these comments, L2 norm, and here I put L1 norm. L1 norm and L2 norm are general terms for Ridge and Lasso. So if you see those terms anywhere, that's what those are. So I just want to go up real quick before I get to the last thing and talk about that. So let me draw a sort of like a mind map, a flow chart. Okay, so under regularization, you have many different kinds. Two of the kinds that we talked about today are L1 and L2 norm. And L1 and L2 norm are basically called L1 and L2 norm because of the penalty term. So let me scroll up to the penalty term. Hopefully it doesn't block anything. All right, let's do this. So L1 just means that you're taking the absolute value of a coefficient or a parameter. L2 means that you're taking the square. There's actually like L3 and L4 as well. And basically it's the same thing. Instead of doing a square, you can take like cube or to the 4th power. That's what L1 and L2 are. And for different models, and for different regularization models, you can do the same, pretty much the same thing. Basically, Ridge and Lasso are the specific ones for linear regression. So if we're just talking about terminology, Ridge is a type of L2. Ridge is a type of L2, and then Lasso is a type of L1. And then there are actually other different kinds of L1 and other different kinds of L2 that we will see in the other models we'll talk about next week. So in terms of terminology, that's what it is. Regularization, L1, L2, there's also other kinds. And then Ridge and Lasso are just the specific ones to linear regression. Cool. All right, so finally, the last thing to talk about, pros and cons, and then this is when I'll talk about assumptions as well. So for Ridge, some benefits or differences between Ridge and Lasso. For Ridge, we're shrinking down prediction variables effects instead of deleting or zeroing them. Oh, hold on, I have like a grammatical error there. Okay, instead of deleting or zeroing them. And also, when you have features with high multicollinearity, what's really neat about Ridge is your coefficients are automatically spread across them. So let's say, I think we had like square foot living and square foot living 15 were two variables that were highly, highly correlated in the last data set. In a lot of like your, I guess, initial models, because those are highly correlated, one might have had like a really high p-value, therefore redundancy, and you end up dropping the one. When you're doing something like Ridge, because of the nature of its cost function, it will automatically take the coefficient value and spread it across the multicollinear values. So it's pretty neat. You don't have to check for multicollinearity if you're doing Ridge or Lasso, which is pretty neat. So
you wouldn't have to get rid of those features, you're saying?
Yeah, you wouldn't have to get rid of those features, absolutely. I guess one downside is because it includes all features, it can be computationally expensive if you have a lot of variables. So it's kind of like a balance, and it also really depends on your context. Like if you're dealing with like 1,000 feature data set, maybe you use Lasso to do some quick first round feature selection, or maybe you have other methods of, I don't know, classifying the different features that you have, or like maybe you know that you definitely want to keep like a subset in another subset you can try later on. Many different methodologies. As you know, it's a very iterative process anyways. But yeah, Ridge can be very computationally expensive just because it has a lot of variables. And with Lasso, same thing with multicollinearity. It does the exact same thing. It will also spread out your coefficient values across different features. And the pro of Lasso, again, is it just does the feature selection for you automatically. But yeah, that is Ridge and Lasso, which are the specifics, again, the specific kind of regularization that you can do for linear regression. If you found some overfitting in your last project, maybe you want to try it out. Not necessary, of course. But for most of the models that we're going to talk about next week and going forward, there's usually some method of regularization. A lot of times it is built into the model itself, but we will get to that when we get there. Cool. With that, any questions before we end for the week? Awesome. Let me stop the recording here and we'll do our weekly check-in.